finish instructions, which is very different from how fast how long it takes to actually complete an instruction. Okay. On the right-hand side, we have a control system. You can see there's a closed loop here. And so that closed loop is what makes latency important. Throughput is important. It tells you how much compute you can do. But if you have high throughput and high latency, which a lot of processors do, then that's going to cause problems in the control system. And in fact, we know from classical control theory that if you have enough delay in the sensor, that you can actually drive the entire control system unstable. Okay, so we care about, in the case of a perception system, the time it takes to go from raw data out to analytical results. Okay, one could ask, well, then how much latency is tolerable, right? And control theory, digital control, doesn't give us quite as much guidance as we might like. A typical rule of thumb is, maybe 10x the highest rate in the system. There aren't a lot of analytical results that'll let us derive exactly what latency makes sense, but we can use some well-crafted experiments to help us explore that design space and figure out how latency affects the overall performance of the control system, because that's what we really care about. We don't care about the computer itself. We care about the control system that has the computer in it and the computer vision system in it. Okay, so the standard way you do perception these days is with neural networks, and there's a whole bunch of work out there on neural networks. These are digital computing machines, at least the typical ones are, there are several parameters we can use to describe the computational load that a neural network creates. One is the depth of the network, the number of layers. Another is the size of the convolutional network, and then the overall number of parameters. Okay, so here are some sample neural networks, and I've shown the numbers for both convolutional layers and connected layers. You can see there's quite a bit of variation. Okay, but in general, neural networks will often add depth in order to try to improve the accuracy of the perception. They might, have more parameters as well. Well, and of course, depth to some extent implies number of parameters. Okay, so the convolution step is a big part of the computational load of a neural network. On the one hand, there is an embarrassing amount of parallelism in convolution. On the other hand, there are data dependencies. Okay, so the results of one layer are fed into the next layer. That data dependency has to be obeyed. So within a convolution, for example, you may be able to do a lot of things in parallel, but there are certain data dependencies that need to be satisfied in order to make sure the neural network actually works. Okay. There's been a lot of work over the past few years in making more efficient neural networks. And this generally implies some amount of hardware design, right? The two major methods are sparsity, that is zeroing out in certain parameters so that you're multiplying by 0, which you don't have to worry about. And the other is numerical precision. How much accuracy do we need in the input parameters and in the result? And there's quite a bit of work out there on both methods. I will say, however, that many of these methods assume that they want to keep the accuracy of the perception system constant. They want to improve the latency, reduce the computation time, but not affect accuracy, maybe 1 or 2%. But is that necessarily a constraint, right? If you're using this, open loop to classify photos on the internet, maybe you want to have the same level of recognition accuracy. But if you're using it as part of a control system, once again, what you care about is the accuracy of the control. Is there a trade-off to be made between the accuracy of perception, how well it identifies the location of something that's in front of your vehicle, for example, and the speed at which it does it? Because if there is such a trade-off, that should allow us to further optimize the network. And we're still working on some of these questions, but we think we have some interesting observations. Okay. So, treating the system as a whole, perception and control, allows us to make trade-offs between latency and hardware cost. In a lot of cases, perception is treated as a separate design task. And if you're designing an autonomous vehicle, a control system, I think that leaves some options on the table. Okay, so we're interested in more holistic view of how perception affects the overall performance of these control systems. Okay, and the good news is that we use feedback control because it's pretty good. Okay, it doesn't rely on a whole bunch of knowledge, accurate knowledge of the physical plant or of the sensor. Okay, wrapping feedback around a plant is very robust to changes in the plant itself. It's robust to changes in the sensor. Okay, so that robustness suggests to us that this trade-off actually exists. Okay, so now let's get down to our first piece of work. Krishna is working on drone-to-drone tracking as an application area. So the idea is, as it shows in this scene, you've got your drone, which is the one closer to the front, and then it's trying to track a drone that's farther out. Okay. This is a very nice abstract problem. It's a good way to think about control, right? You've got motion. You can fly your bird in 3 dimensions. The target drone can fly in 3 dimensions. And if you track it perfectly, it's always right in the middle of your view. Okay. This is also a fairly practical problem, right? There are situations when we want to follow a drone or perhaps even take it out. For instance, drones that are invading civilian airspace, not to mention, military uses that we've seen around the world recently. Okay. So this is more challenging in a lot of ways than the ground problem. I think you don't have pedestrians in the middle of the air, but it is challenging in a lot of ways. And we are very concerned about computational cost here because we're flying. Every erg of energy we use in perception is energy that we can't use to fly the bird and run the mission. Okay. So the energy consumption of the platform affects the weight of the vehicle as well as the duration of its flight. Okay. So Krishna set up a co-simulator, which is a neural network in the loop simulator. So we've got AirSim, which is a widely used drone simulator, and it's set up so that we can insert ourselves in the loop of the simulator. So the simulator puts out a frame for the current state of the simulation. That is sent to a neural network controls perception system that identifies the target in the image, or if it's not there, will give both location as well as a bounding box that shows how big it is and presumably how far away it is. That's given to the control system, which decides how to fly, how to set the controls on the next step, the throttle and the flight surfaces and so forth. And then that's given to AirSim for the next step. So you can actually fly a simulated fly a neural network inside this environment. Krishna has also done some live tests with real drones. I'm not going to be able to talk about that here. Now, as an example of the difference between simulation, well, of talking about something and doing something, in order to get this work, Krishna had to take the Intel compute stick that he used to implement the neural network, first plug it into a Raspberry Pi, and then plug the Raspberry Pi into the drone controller. Okay, that's because the drone has no driver for the Intel compute stick. Okay, but it does have a driver for the Raspberry Pi. And so by transitivity, we can have the two talk to each other. This is not ideal. This is not what you do in the real world. But if you want a student to graduate in a finite amount of time, these are the things that you do to try to get some results. Okay, so let's get to the actual experiments. We looked at two networks, faster RCNN and SSD. Faster RCNN is generally pretty accurate. Despite the name, it's slower than SSD. Has longer latency. So SSD is somewhat less accurate, but it is faster. Okay, so we will use both of these in simulated experiments where we have a target drone flying some trajectory and we want to follow it, and we want to see the error in tracking from the perfect track to what it actually does. Okay, so in this experiment, the title gives you the speed of the simulated speed of the target and the neural network, which in this case is RCNN. And in this case, we could run RCNN on our platform at up to 3 hertz. So Krishna ran 3 experiments, a perception rate of 1 hertz, 2 hertz, and 3 hertz. At 1 hertz, which is blue, it didn't do anything. It just couldn't run at all. 2 hertz, which is orange, the up and down arrows show where it lost track temporarily and then regained track. And you can see it had a fairly hard time tracking the target. And then in about 26, 27 seconds, it completely lost track. You increase the sample rate to 3 hertz, and it lost track sometimes, but it did a better job, and it completely lost track at about 48, 49 seconds. Okay, so that is with the more accurate network. Okay, now let's go for the faster, less accurate network, and we were able to run this at 5 hertz, 10 hertz, 20 hertz, and 30 hertz. So 5 hertz is the blue, and you can see it was struggling a little bit to keep to maintain to be able to see the target. It goes in and out. There's a fair amount of error there. At the higher sample rates, there's a little bit of missing the perception, but it generally does pretty well. And going faster than 10 hertz doesn't really help you. Okay, you have the same amount of error for 10 hertz, 20 hertz, and 30 hertz. Now you can see this hump in the error curve. That's because of the target is maneuvering, and the control system is a classical control system that isn't able to track perfectly, even if you have perfect perception, right? But it's doing pretty well, and speeding up the network beyond a certain point doesn't help. Okay, so we can see this a little more clearly in a different format. So the columns are the sample rate we're running at, and this is for RCNN, and the rows are the velocity of the target. And so you can see that at basically at 5 meters per second, none of these sample rates were good enough to keep track of the target. We move to the faster network SSD, and we can see this interesting shape here where there is a trade-off. Okay, as we increase the velocity of the target, going 5 to 8 to 10 meters per second, we have to increase the sample rate in order to be able to continue to track. Okay, so there's clearly a cliff function. Below a certain rate, the system doesn't work at all. Above a certain rate, improving perception rate doesn't really help you. Okay, so we think this is an interesting observation, and we're working on follow-ups to better characterize this design space. Okay, so now I'd like to spend a few minutes talking about flash LiDAR and how to use it effectively. Our student Deep Samal did a bunch of experiments and developed some algorithms. This camera is part of our experimental setup. There's actually two cameras in the picture. On the left side is a flash LiDAR unit. On the right side is a regular RGB camera. The flash LiDAR takes an entire two-dimensional picture at once. If you've seen pictures of autonomous vehicles driving around, if they have an ice cream cone on top, that is usually a scanning LiDAR in which you have a head that rotates around. So the good news is you get a 360-degree view. The bad news is it takes time to scan, so you don't have a snapshot of everything. This this camera takes an entire two-dimensional picture. Okay. It is lower resolution than a scanning LiDAR, but it gives you a snapshot. It also runs at a higher frame rate. This one sample Velodyne scanning LiDAR runs at about 10 frames per second, and our flash LiDAR runs at about 25 frames per second. Okay, as part of our experiments, we put together a data set called the CAMEL data set. That's at camel.godtech.edu. We have visible and infrared imagery on pretty much everything, and LiDAR on some of them. Okay, so this is mostly urban scenes around Georgia Tech. This was, all of these videos include ground truth for several different categories of subjects. I believe it's people, cars, bicycles. And the students put an incredible amount of effort into generating those ground truth labels. Okay, so interpreting LiDAR, getting reliable results out of LiDAR is difficult. There's a lot of data. It's much lower resolution than an RGB camera would be. And so you want to develop some methods in order to try to improve the results for detection in LiDAR data. And the methodology that Deep came up with is to use two detectors in parallel and then fuse them. So the top one is a primary detector, typical neural network. And then the other one is another type of detector, and he looked at two different methods, as we'll see, that are generating masks that identify what computer vision people call foreground. Now, foreground actually means object of interest or area of interest. If you're a theater person, you know the foreground means toward the front of the theater, toward the front of the stage, and background means back of the theater stage. Computer vision people mean interesting, not interesting. Okay, so the idea is to use this foreground mask generator as a check for the primary detector and use that to improve the results. And so the goal here is to track objects in the scene, and these are called tracklets, because let's say a person walks behind something and then reappears. This kind of tracker won't be able to join those two together into a large track. It'll create two tracklets, okay, that another step can fuse together. Okay, so Deep looked at two methods. One is model-based, which is, has more information about what the scene might include. So it's not a data-driven algorithm. The other is a self-supervised, fully connected network, which is a fairly compact network. It's trained on data, and it's self-supervised training. So you don't need labeled data in order to train it. Okay, so let's see. I don't think it's going to let me play this video here.
Yeah, I'm sorry, we lost the camera for a moment, but we are hearing you very well. Please.
Yeah, no, but I mean, I have a video on this slide, and it won't let me play it.
It won't let you play. Well, that's a different story. Just a second, I'll check with the technician. I'm sorry, Professor Marilyn.
Well, okay,
let me able to play. May suggest that you step forward and then we return to the video as soon as the technician finds out what the problem could be.
Sure. Okay. So we can use this model-based method to identify some pixels in the frame that that might be of interest, and then basically use that to override the original detector and say, I think there's something here. Okay. So the other approach is a fully connected network, which we see down toward the middle. Most of the rest of this is, at the top part at least, is the training process for that fully connected network. So given the trained network, you send the LiDAR imagery into the network. It produces a mask that says this pixel in the frame is interesting. Okay, once again, we have another video there. So the model-based method is more computationally expensive, interestingly enough, than the fully connected network. It's about twice the computational load, 0.35 gigaflops versus 0.17 gigaflops. And all this is on sort of a mid-range video card. So the model-based method is more expensive. It's also a little better. This slide has some stills that will at least give you an idea of what's going on. So the RGB frame gives you an idea of what the actual scene looks like. These are people walking in front of our building at Georgia Tech. And you can see that the LiDAR frame has identified some people here. With confidence metric, it missed one or two people. You can see that the size of the box gives you some idea of how far away that person might be, assuming that all people are roughly the same size. Then we have below frames from the model-based detector and the self-supervised detector. In both cases, they identified pixels that they thought were interesting. The model-based detector detects this thing over on the far left, which is over here, which the baseline algorithm did not. The self-supervised method identifies a fair number of things that the model-based does, but it also identifies a bunch of other things that in several cases are not actual people or targets of interest. For instance, it seems to identify these poles here, which are part of this statue over here. So the self-supervised network, although faster, is not quite as good. And we can see those results in the overall tracking performance. So false positive, false negatives, number of IDs, and then the measure of tracking accuracy metric here. So the best method is the supervised network plus the model-based method that gives us the highest accuracy. The supervised plus the fully connected network is a little less accurate, and then that's noticeably more accurate than just the supervised network only. Okay. There is some cost in false negatives to doing this. Oh, excuse me. Sorry. There is a decrease in false negatives, but there is an increase, a small increase in false positives. Well, significant increase in false positives. Okay. So actually, did your team make any progress on those videos?
Unfortunately not. I'm sorry.
Well, that's okay. That's okay. Well, so this is basically what I had to say. So we're pursuing perception as a component in a larger system. A traditional control system, perhaps a neural network-based control system, but the requirements on perception do not live in isolation. They should be identified based on the needs of the overall control system. And so that leads you to consider accuracy and latency as a trade-off space. And we've seen parts of this trade-off space play out in our experiments that Krishna did. We have more work to go to more fully explore that design space. And we also looked at the challenges in effectively using LiDAR to detect objects for tracking. And we saw that self-monitoring systems can improve the overall accuracy of LiDAR analysis. So that's what I had to say. Thank you very much. Are there any questions?
Thank you very much. Let's thank Professor Marilyn. So really sorry for these difficulties here. We don't know what happened.
Yeah, these crazy computers,
We fortunately now have plenty of time for discussion. Questions from the audience? Yes. Since this is the only place where we have it live.
Okay. Thank you. Can you hear me?
Yeah.
Okay. So first of all, thank you for the presentation. It was very good. I would like to ask, how did you integrate Raspberry Pi control system, Raspberry Pi based control system with simulation environment?
Well, it's not a Raspberry Pi based control system. Okay. The Raspberry Pi we're using basically is an interface. So I'm pretty sure that for the simulation experiments, he wrote some code, some C code to do, he actually started off with PID controller, and I think some more recent experiments went to LQR control. But that was running, since the simulation's running on a PC, it was running there. Now, when we get to actual flight experiments, the controller for the drone itself is flying the drone. The Raspberry Pi is just glue.
I see. Thank you very much.
Yeah.
Questions? While we wait for more questions, let me start with a provocation.
Yes.
I guess you can see us from here. Yeah. So it's about, let's say, 10, 15 years now that people has been talking about neuromorphic computing to replace all these traditional sampling, quantizing, coding, detecting, then synthesizing results. And more recently, even there are many American universities talking about analog computers to do the same, trying to mimic some of the perception that we have in biological beings. How do you see this research? Is it taking too long to become a reality? Is it still coming? Will it target a different scope of the problem?
Well, I think that perception really is just part of the game, and that accuracy and perception itself is not the big picture. I actually think that I think that we could do a better job of building autonomous vehicles that have a more complete view of what's going on in the scene, complete understanding, a mental model that they use to understand the scene so that they can figure out how they should move. Okay. I think that, some of these new methods for computing neural networks, whether it be the spiking or, some novel devices, those are certainly interesting, particularly if they can help us with latency. But I think that the standard view of an autonomous vehicle is a pipeline of tasks where you go from sort of overall goal of where you want to go down to sort of frame by frame control. And I think that things should be a little more tightly integrated than that, and that people need to understand the scene as a whole and put their attention on things that are most important. And focus of attention is another thing that Deep has looked at. With I think in pretty much any vehicle scenario, you have a cap on how much computation you can do in a given amount of time, right? You don't have time to send it off to the cloud and wait to get an answer. You have a certain amount of compute power on your platform, and you may need to change where you put that computational power at different times during the session. Okay, you may want to attend to part of the scene more carefully if you think something important is happening and something that needs to be reacted to quickly is happening. Okay, and so sometimes you may be taking a general view of what's going on, and sometimes you may be focusing on a particular part of the scene. That's what good drivers and pilots do, and I think we need to do more of that inside vehicles as well.
I definitely agree, and I guess this last remark of yours, it doesn't really bind to neuromorphic computing. It can be applied to any ordinary pipeline. You first do it more coarse view to find features that are interesting, and then you go the fully neural network analyzing just part of the image that looks to be interesting. Yes, this could be a way to speed up. We've been
You dropped out. You dropped out. You dropped out. You dropped out. Dropped out. I can't hear you. I can't hear you. I can't hear you.
Yeah, now.
Okay, there.
The technical problems of the video, we are having network problems. We almost lost you.
Yeah. Okay.
Next question. So I've been talking to some of the students about the real timeness of this kind of perception system. In some sense, you showed us that it's a trade-off, but how do we get to know what the minimum is? Where is the bar? How do I know that I will be capturing the events and the scenes that are really meaningful for steering an autonomous vehicle?
Well, I think you have to be able to characterize the scene, right? Just say there's not going to be, you need at least this kind of processor in order to do anything. It depends upon the complexity of the scene, how many cars there are, how many people, how many other things, how fast they're moving. To some extent, the visibility might play a role, right? If you're dealing with fog, that's going to cut down your accuracy, so you might want to move more slowly and carefully. So I think you need to carefully define the scenarios. And then, as I say, I don't think we have a good theory on how to derive the accuracy or the latency we need, but we can do experiments that characterize it.
But making all the experiments at design time while you are trying to build the platform, it's quite complicated. And I guess that's why so many people look for the most expensive GPU with lots of computing power. It doesn't matter how much energy they spend, because at design time, trying to conceive what would be the worst scenarios and making a system that only works on non-extreme cases. I mean, many of the computer vision people in Brazil, they simply don't like these ideas of being scalable, having to negotiate the kind of control they are doing. They simply try to bring aboard the most expensive GPU with a lot of power, big machines, big batteries, to be sure that they can account for everything that will come. If we could move some of this decision to design time. Sure.
Well, okay, I understand that a lot of computer vision people just want to overload systems, but I think they're wrong for two reasons. One is that no matter how much compute you put in your vehicle, I can overload it. Okay, so assuming that you can handle everything is going to fail at some point, right? And you're better off having a management system, a runtime management system that can control things and degrade gracefully and understand when it's reaching its limits. Okay. The second is that, as I said before, all this compute costs weight and it costs power, and both of those will hurt the operational characteristics of the vehicle. Okay. Make it run slower, make it be able to go less far, and perhaps not even take off if it's a flying vehicle. Okay, so I don't think that we can brute force our way out of this.
Sure, thank you. More questions?
Yeah. Can you listen to me?
I didn't hear that. I can hear you now.
Okay, thank you. So our team was working with a small, very limited wager robot, and we came to experiment with YOLO V7 to do some tracking from, in this case, stopped objects for autonomous robots. What I wanted to ask you is if your team is working with other models than faster RCNN and SST. Have you experimented with other models, and how was the performance considering it?
We've done a little bit of work with other models. We're also, considering designing some of our own networks. I don't have conclusive results to share as to what network is best, right? It also, as we saw, when you're dealing with LiDAR or with radar, then that's, you need different networks entirely there. So I don't have anything conclusive to tell you. I think, you should feel free to design your own neural network. You don't have to just use somebody else's.
See.
That's not easy, but you have the freedom to do that.
Yes. Thank you very much.
Absolutely.
Another question coming from students from Florianopolis. They are looking for ways to decouple the perception timeliness from the control timeliness, and they come up with some waypoint data structures which bring not only the geographic or the geometry of the path, but also the state of the vehicle, the desired state of the vehicle. Supposedly, you did something similar for the drones there. How was this done in the project? How did you decouple the perception from the low-level control steering the motors, the engines in the drone?
Well, if I understand the question, that's we didn't decouple. Quite the opposite. First off, the waypoints require knowing the path in advance, right? And we didn't know that. In the case of the drone following experiment, we're trying to follow a drone, and the target doesn't know what the chase drone doesn't know what the target's going to do. It just has to react to what it sees. Okay.
But there is a connection between the perception, the output of the perception, and the input of the low-level control.
Well, yeah, you have a bounding box.
Okay.
Right.
You just center the targets in a bounding box, and you try to
mimic. The bounding box is where the target is. The center of the frame is where you would like the target to be, right? So the control system tries to move the chase plane in order to get the target in the middle of the frame.
But wouldn't it make sense to have these quick reactions model as a short-term path that should be followed in order to avoid extreme maneuvers or in order to avoid dangerous maneuvers?
Well, the dangerous maneuvers thing, I look largely as a higher level control issue, but we are generating. Look at it this way: we have a digital control system where we have a command input at every sample time, right? That command input is generated from the bounding box of the location of the target drone. Okay. Now this is a very pure scenario here, right? And in a more typical use case, we would have a little more structure in the scene. But even so, you may need to adapt to what's going on in the scene. That's particularly true in ground vehicles in urban scenes where you have to deal with other cars at close range, a whole bunch of pedestrians who are doing all sorts of crazy things. But it could also happen in a flying scenario, particularly when you're in the departure arrival phases of flight. So yeah. If you have advanced knowledge, you can use that to help decouple certain decisions, but you can't always assume that everything is known in advance. And that's part of the challenge of building an autonomous vehicle. It's not just a simple-minded object. It has to be able to react to the environment.
Okay, thank you. One final question. So let's thank Professor Marilyn Wolf once again. Thank you very much for being with us.
Thank you so much. I really appreciate it. Thank you very much. Okay.
We help. Hopefully, we will see you soon in Brazil in person.
Absolutely.
In the future for the next edition.
I would love that.
Thank you very much.
Take care. Bye.
Bye.